continuing work with this section. Just really quickly before we jump in and do another one. And we still have plenty more. Again, there's a lot of experience that we want to get here because first just getting the right trig substitution, but then also continuing to get more practice with the trig integrals that are left behind. We'll do a whole nother bunch of integrals here. For pretty much all of these, you're not going to find good alternative choices. There might be something that you might eventually get to work, but most of these are really, really kind of more of the, again, any other form would be a lot of work. The trig substitution is your best bet. But just one very, very quick thing to point out. When we did number 4, we had this divided by this expression. Just to realize if it was x cubed times this expression, it would have worked out almost the exact same. We would have had 64 sine cubed times 4 cosine times 4 cosine. So these wouldn't have canceled, but we would have had sine cubed cosine squared instead of just sine cubed. Still would have needed the exact same substitution. Sine cubed cosine squared, one sine left over, and then converting all the other sines into cosines, still would have used this u substitution. So just the fact, I'm just trying to point out here, this was division, change that to multiplication, same exact process, works out equally in the exact same way. Okay, so now looking at number 5. Okay, we still see that same radical expression. And actually, let's even make that a 7. We've got radical 7 minus x squared. Now it's in the numerator. I also have this x squared in the denominator. I see ugly division. If I tried making a u sub, u as what's under the radical seems like a good place to start. But the derivative gives you a negative 2x. It doesn't even cancel here. It would actually combine. So there's just all kinds of things making this a tough problem, and none of our traditional techniques can work. But after we run through all those options and see none of them are working, we go back to this trouble. It's not just a radical, it's a radical with a squared minus x squared. Now you might look at 7 like, well, wait, we had a squared was 16, so a is 4. Or some of the problems in the book, if a squared is 9, then a is 3. But you realize the number doesn't have to be a perfect square at all. If this needs to be my a squared setup, well then a would just be the square root of 7. So we're still using that first form. This is still another a squared minus x squared, so we're still using a sine theta. But just notice my a, there's nothing wrong at all with a being the square root of 7. Dx, same thing, take the derivative here. So I get the square root of 7 cosine theta d theta. We make our substitution. In here, I get radical 7 minus 7 sine squared. The denominator, don't forget again, that x is getting also plugged in here, substituted. So this squared would give me a 7 sine squared here. And then the dx becomes the square root of 7 cosine. Okay, focus on the radical part. This becomes the square root of 7 times cosine. Now, some people, how much do you need to do here? Again, maybe off on the side. Let me do it. It's still a little early for a lot of us. So to see how that happened. And again, maybe instead of doing all that work in the middle of an integral with a lot going on, to do a little on the side. 7 comes out. You're left with 1 minus sine squared. 1 minus sine squared becomes cosine squared. And again, before we had something like the square root of 16 cosine squared, the square root of 16 was 4, and the square root of cosine squared is cosine. But here, the square root of 7, we don't want decimals, we don't want our calculators to get an approximate. We'll just leave that as the square root of 7, and the square root of cosine squared is cosine. So, the square root of 7 times the square root of 7 is 7. Cosine times cosine, cosine squared, over 7 sine squared. Well, what do we do from here? First thing, the trig substitution is done. It has once again served its purpose. The trig substitution was meant to clean this up, and it has. Everything else I simplified. Well, let me at least cancel off the 7s. So I've already cleaned up the remainder, and now it's up to us to figure out how to handle this trig integral. Well, cosine squared over sine squared. Again, we got to try. We don't have the odd power. I can't kick out one trig function and convert the others, so we're not going to get that nice u sub here. But what else can we do? Well, we notice cosine over sine. That, by definition, is cotangent, but they're both squared, so it's cotangent squared. Is that better? Well, so far, no, because that's still not a known trig antiderivative, but I'm one step away. Remember, even though we're focusing a lot more on these Pythagorean trig identities, there was a third one. We had 1 plus cotangent squared equals cosecant squared, so this equals cosecant squared minus 1. Is that a good move? Well, yes, it is. And it is a good move because we know the antiderivative. The antiderivative of cosecant squared is negative cotangent, and then the anti of 1 is theta. Careful, everybody. It's so easy to put an x here and then forget to do the back sub work, but we've already converted everything to theta, so that's why we just get a theta here. And now, how do we finish this? Still, well, this, we've got to solve directly for theta, and here we're going to need the right triangle. But it comes back to here, x over the square root of 7 equals sine. Make my right triangle. Again, this is just for reference. So I just always make the same right triangle. So I always keep opposite, adjacent, hypotenuse in the same spots. So my opposite is x. My hypotenuse is the square root of 7. This squared plus this squared equals this squared, and that will give me 7 minus x squared under the radical. Just to show you that, so I'm literally getting x squared plus blank squared equals radical 7 squared. That's 7. Subtract the x squared over square root. Technically, we get the plus or minus, but just thinking of this as distance, we just get the plus. Maybe one more step. Maybe you say, well, I know tangent is opposite over adjacent, so cotangent is 1 over that, the flip. So tangent will be x over radical 7 minus x squared. Cotangent would be the radical over the x. Minus theta, we'll take that one step further. Finish solving for theta with inverse sine of x over radical 7. Not an easy problem. Tough in the first place, but the identity, I pushed us a little bit by making a squared not a perfect square, so a has this radical component to it. But outside of that, this is still a pretty straightforward trig substitution. It was just the trig integral that was still tricky. So again, we still get some more experience. We talked about something like this in 7.2, but we didn't quite see exactly this, but we did almost the same thing. We did the integral of tangent squared, and we made basically the equivalent substitution from the identity. So like I said, not the exact same, but close enough to one we've done that with a little work, we could think to do that. And is that a good move? Yes, it is, because now we have 2 known antiderivatives. Okay, continuing, number 6. Let's look at the integral of 1 over 9 minus x squared to the 3/2 power dx. Now this one also looks tough. But this one looks a little bit tough, but we still have to kind of realize a little bit about the overall setup. It's got the perfect a squared minus x squared, And the 3/2 power, well, the half in that denominator, it is a square root. This is the same thing as this. So it still has the same motivation. That's why initially I started off by just talking about trouble with those three expressions. That's the reason I leave off the radical right off the beginning of this. It's almost specifically for problems like this. Because some people see the radical on that initial chart, and if they don't see the radical in the problem, to them it's like trig substitution is not a possible option. But to realize that is this, so that is a possibility. So I would hope we'd see it more from this form and then make the connection, oh yeah, there still is a square root here. And this, one more time, we're still in the a squared minus x squared. I promise we'll do others that are not always using the sine form, but as you might expect, sine and cosine are the most common trig functions, and the x equals a sine theta tends to be the most common trig substitution. So that's what we get here. We get x is 3 sine theta, a squared is 9, so a is 3, dx, 3 cosine theta d theta. There's no extra variables here, so we're just making clean substitutions here and here. 9 minus 9 sine squared to the 3/2, or again, maybe you prefer to keep writing it like this to help your cleanup, times the 3 cosine theta d theta. We're working on this. 9 times 1 minus sine squared becomes 9 times cosine squared. But again, it's the 3/2 power. First the square root, and I get 3 cosine, but it's still being cubed. So now, putting this together, this is in the denominator. 3 cosine quantity cubed, so that's 27 cosine cubed. I've got a 3 cosine that I'm just going to slide into the top. Once again, the trig substitution has served its purpose. Now the radical is gone, right? The square root that came from the 3/2, the halves part, that is now gone. So, and again, there are no extra x's here. The trig substitution has done its purpose. It's up to us to finish this. Well, the 3 over 27 can reduce a little, kick out in front. Cosine over cosine cubed. I could still cancel 1 cosine. Still for a moment might feel like we're stuck. Again, this one, definitely through some experience, we've seen exactly that before. 1 over sine squared is cosecant squared. 1 over cosine squared is secant squared. Is that a good move? Yes, it definitely is. It's a known antiderivative. The 1/9 pushes along. The anti of secant squared is just plain simple tangent. But I still have to back sub. And even though this was all the 3/2 power, not just a square root, that doesn't matter one bit. Still coming to here. X over 3 equals sine my right triangle. X over 3 equals sine. Radical 9 minus x squared down here for the adjacent side. Tiny little thing to notice, I said before that missing side should match the motivation, and that completely does. The motivation to use this trig sub wasn't because it was the 3/2 power, it was because the square root that was a part of it. This motivated the trig sub, and that's exactly what we ended up for that missing side. And we wanted tangent here, so opposite over adjacent, x over the square root of 9 minus x squared. Very quickly right here, don't rationalize this, everybody. There's no good reason to do that. I know, especially going back to like pre-calculus and some of the trig classes, having a radical in the denominator, it's not wrong, it's just bad form. So having 1 over the square root of 2, you should multiply top and bottom by square root of 2 to rationalize. You could do that same thing here, multiply top and bottom by the square root of 9 minus x squared. It's just unnecessary, especially if you wanted to check your answer. If you wanted to check your answer, take the derivative. There's no trig at all. Take the derivative here, it will match. And you don't need trig functions at all to see that. But if you start rationalizing, now you get x times the square root of 9 minus x squared divided by 9 minus x squared. You are now mixing product, quotient, and chain rule all together. Whereas this one, yeah, there's some quotient rule here and some chain rule, but it's still better than doing all three. Okay, let's keep it going. Numbers 7 and 8 are going to be a little bit similar. Number 7, let's make it the integral, and let's make it x squared plus 9 to the 3/2 power. Plenty of conversation about the 3/2, recognizing it's a square root. The big change here, we're no longer using x equals a sine theta. We're not in the a squared minus x squared form. We're in the x squared plus a squared form. And whether it's x squared plus 9 or 9 plus x squared, same thing. Now we will use x is a tangent of theta. So dx will be 3 secant squared. Substituting that in, we get 9 tan squared. This is the first time we're seeing this one, so I'll write it all out. 9 tan squared plus 9 to the 3/2, which again, maybe you want to write as the square root quantity cubed. Dx is the 3 secant squared d theta. Working down here, 9 out in front, tan squared plus 1 becomes secant squared. And just like we saw in number 6, start with the square root. I'd get 3 secant, but then I cube it. I will get 27 secant cubed. Everybody follow so far? Again, there's several bits of work here, so again, make sure you write enough out. I said several lines, but I only wrote out 2. So off on the side, pulling out a 9, tan squared plus 1. Tan squared plus 1 is secant squared. The square root of this is 3 secant, and then cubing. Finally got that, and all that is still in the denominator. This is in my numerator. And so this is kind of similar to the previous one. We still get a lot of nice things canceling, but one more time, right here, the trig sub has done its job. The trig substitution was meant to clean up this radical, and it did. So the rest is on us. 1 9 out in front, 1 over secant. And now that looks like trouble, and be careful. We know the antiderivative of secant, but this is 1 over secant, which is cosine. And we definitely know the anti of that. The anti of cosine is sine. And I still have to back sub. But now this is my initial information. So I'm going to have x over 3 equals tangent of theta. Still same right triangle setup, but this time it's tangent, opposite over adjacent. This squared plus this squared equals this squared. Use your Pythagorean theorem. It does match the original motivation, so a good confirmation. And we finish 1 over 9. Sine would be opposite over hypotenuse. I mean, we're a good way through this lesson right now, and I really hope you've realized how much the basics of trig are really necessary here. The derivatives, antiderivatives, the identities, basic cleanup. I mean, that's why these can be really, really tough problems. And if you're really struggling here, some people can identify. It's not the trig sub they're struggling with, it's the work after. And for a lot of that, hey, it's great to get extra practice in 7.3. These trig subs lead to these types of integrals, so that's a good place to get practice. But you can always go back to 7.2. plenty of good practice there that should prepare you for anything that might possibly come up after you clean up whatever's left with your trig. So, not so bad here. This was pretty messy initially, but after we cleaned up, it didn't look bad, and especially after we got to here, a very nice, quick, easy finish to this problem. Number 8, still one more that's still kind of similar. Let's look at 1, and this time let's do x squared minus 9 to the 3/2 power. So in number 6, we had an a squared minus x squared. In number 7, an x squared plus a squared. And now this is finally an x squared minus a squared. This one requires x is a secant theta. So dx will be 3 secant theta tan theta d theta. Notice you don't get to pick the trig sub. That's where some people think things like, well, I like the sine trig sub because the dx is just a simple cosine. The dx for tangent now gives me a secant squared. The dx for secant gives me both a secant and a tangent. You don't get to pick that. That is what it is. This is what's necessary to clean up this expression, and this is part of what's left that, again, we just have to plug in and deal with it. So when we plug that in, 1 over 9 secant squared minus 9 to the 3/2. That's going to become 9 tangent squared to the 3/2. And I'm doing the substituting part a little quickly. Again, know yourself. Plug it in, be thorough. 9 secant squared minus 9. Pull the 9 out. Secant squared minus 1 becomes tan squared. And now we're all back on the same page. The dx, 3 secant theta tan theta d theta. Down here, the square root makes us 3 tangent, but then I cube it. I get 27 tangent cubed. On top, 3 secant tangent. Still a good bit of mess here. Tangent, the 3 and the 27, we can get the 1 over 9 out again. 1 tangent cancels, but now we're left with 1/9 out in front either way, out in front of the integral or just the front of the integral, secant tangent squared. Where do we go from here? The answer is sines and cosines. That's really, we're not in that perfect secant tangent situation. If I try and substitute this, tangent squared equals secant squared minus 1, doesn't help. Now the denominator gets more complicated. I can't separate my fractions. That doesn't help. I can't do any good u sub. If u is secant, du is secant tangent. If u is tangent, du is secant squared. Nothing good is happening. So this is kind of almost a worst case scenario, getting everything back to sines and cosines. Secant is 1 over cosine. Tangent squared in the denominator would be cotangent squared in the numerator. So I get a cosine squared over sine squared. 1 cosine cancels. So all of this cosine over sine squared. Oops, not to forget, I should still have my d theta here. Still definitely need it here. And finally, we're in a better spot. And you might say, what's better about this than we were here? Now we've got the good u sub. Because now I can let u be sine and du is cosine. 1 trig function raised to a power and its derivative ready to cancel. So this still puts us back into our more friendly situation. The other funny thing, everybody, you could keep working this. This is cosecant cotangent. That's the other alternative. So this was definitely not obvious. It just required us to keep manipulating. We continued to manipulate until something good happened. Started in terms of secant tangents. That was about as clean as it got. Got to sines and cosines. Here, That will work, but I'm going to finish it by realizing cosine over sine times 1 over sine. I'm getting cotangent times cosecant. So that has an antiderivative of negative cosecant. Again, it works. If you do this as u as your sine, you'll end up getting negative 1/9 u to the negative 1, and sine to the negative 1 power is cosecant. So this u sub or this continued trig manipulation still gets us to the same answer, and I still have to back sub. If you made this u sub, you already back subbed once to get it to theta, but still have to back sub to finish. And this finish, just to realize, well, if x over 3 equals secant, not a lot of us know secant in terms of the right triangle. Well, flip it. That means 3 over x is cosine. So 3 over x, adjacent over hypotenuse. Use your Pythagorean theorem. This squared plus this squared equals this squared. You'll get the radical x squared minus 9. And now when I back sub, even here I want cosecant, but that is 1 over sine. Sine would be this over this, so cosecant will be this over this. Minus 1/9 x over the radical x squared minus 9 plus c. And both of these. I mean, it's kind of funny, right? If you look, these had very, very similar answers when everything was said and done. This one had an extra minus, this one did not, but a lot of different work to get there. And in both of these, no good reason to take it any further. That was a very good answer to finish. Same thing as that. Any more work would make it more difficult to check any work. So again, a good spot to just leave your work. That is a good, best final answer. Okay, still want to do a few more. Still want to do 3 more problems to, again, get plenty of good experience. So number 3, this will be number 9. Let's look at the integral of 1 over x squared square root of 1 plus x squared. Another very ugly situation. No good u sub to help us. The basics, we've got sort of some division, bad multiplication, inner, outer. If you pick u as your inner, you're not going to get anything good to cancel here. It makes things worse. Again, just all kinds of mess. So what can we go to? I hope you realize, we keep saying it, but all the new techniques, they're not the first things you jump to. They're kind of the last things you jump to. Still, I mean, 7.5 will go through a whole general strategy session, and it's not just general strategy with the new techniques, it's looking at all integrals. So always remember the basics. Can you clean up? What is the problem? Is there even a problem in the first place? Okay, starting with that. Then considering u subs and what are the possibilities there, or other basic manipulations. Then we start thinking about higher level techniques. And for our higher level techniques, trig subs definitely jump out based off of this. This is an a squared plus x squared plus a squared plus x squared. X is a tan theta. And if a squared is 1, a is just 1, so dx is just secant squared. We plug that in, 1 over, we're right off the bat. Once again, we've got an extra variable. This motivated the trig substitution, but we've got extra variables. That has to be substituted there as well. So this just became tan squared times the square root of 1 plus tan squared times secant squared theta d theta. Working, this becomes secant squared, and the square root of secant squared is just secant. 1 secant cancels. So, I mean, right here, the trig sub did its job, and now it's up to us. The rest of the cleanup I have. Secant over tangent squared. Hey, don't look too far. Again, coincidences, everybody. The little things that happen. Number 8 and number 9, completely different looking integrals. But both number 8 and number 9 ended up with secant over tangent squared. So go back in number 8, the two different choices, first getting yourself to sines and cosines, then getting to here and thinking about the u sub, or continuing to manipulate and realizing you get a known trig antiderivative. But either way, the cosine, the secant over tangent squared became negative cosecant theta. Same thing right here. So I'm going to jump to that, negative cosecant theta. There wasn't even any extra numbers out in front. But back substituting, very, very different. Because here in number 8, just because we ended up with this inside the integral, the back substitution at the end will be completely different because of the motivation at the beginning. So here we're going back to x equals 1 tan theta. So x over 1 equals tangent, my right triangle, x over 1, Pythagorean theorem, there's my third side. I hope you realize, everybody, I'm doing that in my head. It's a very bad habit after I tell people that this missing side on the triangle should match the initial motivation that we started with. It becomes a bad habit. People just automatically fill that in. But again, it should be used as a reminder. So I know I'm not writing it out, but I'm doing it in my head. X squared plus 1 squared equals blank squared, and all I did was take the square root, and that's how I got my third side. Again, I want to know about cosecant, so I would start out by thinking about sine. Sine of theta would equal x over radical x squared plus 1, so cosecant would be 1 over that, the flip. The negative is still here. Sorry, I don't want that to look like a plus. That's just a negative. The negative is still here. Radical x squared plus 1 over x. I didn't choose to put the radical term in the numerator. That's just where it ended up. I'm not rationalizing or anything like that. Again, that's just where it ended up, and that is my final answer. Okay, so let's continue. And actually, I think one more good one to wrap this up. Lots of good examples, but let's finish up with number 10. Let's finish with the integral 1 over radical x squared minus 25. Well, not a lot to work with. This one is tempting to think about inverse sine, but realize 25 minus x squared, that can be made to fit the 1 minus u squared under the radical. So 25 minus x squared, you could go back and treat that just like number 1 in the first video and do inverse sine, but x squared minus 25. The order of subtraction makes a very big difference. There is no way to make inverse sine work here by itself. So it's not a known antiderivative. U for the inner part, that's not going anywhere. The d would give you a 2x. There's no extra x's here. So again, we've exhausted our basic options, but I've got trouble with that radical. X squared minus a squared. So x is a secant theta. We'll finish up with one more problem to practice with x equals a secant theta. dx 5 secant theta tan theta d theta. Plugging these in. 1 over. This is 25 secant squared minus 25 under the radical times 5 secant tangent. Down here, this becomes 25 secant squared minus 1. Secant squared minus 1 is tan squared, and the square root of that is 5 tangent. The trig sub has done its job. This cleaned up. What's left? Well, hey, the 5's cancel, the tangents cancel. all that's left here is secant. That's a known antiderivative, not the derivative of secant, but the antiderivative of secant is known, and we still need to backsub. And little things here, backsubbing, well, x over 5 equals secant theta. I mean, this is directly secant. So, I mean, sometimes you can get a little lucky and kind of avoid the right triangle, but here we've got to do more. I mean, other people, they never make the right triangle. They just play games with more identities to do these substitutions at the end. But I think the right triangle, number one, it reminds us of SOHCAHTOA, which is a good thing to remember, your right triangle connections to the trig functions. And secondly, I think for most people, that's the easier way. But I've got to finish this. Most of us, we make this swap. If secant is x over 5, then 5 over x is cosine. So that allows me to make this right triangle adjacent over hypotenuse, missing side. This squared plus this squared equals this squared. So this would be this squared minus this squared, square root, when I solve. And for tangent, opposite over adjacent. And there is your final answer. Just two things before we finish this video. Number one, you have no idea how hard the trig integral is going to be based on the trig substitution that you make. For a lot of us, when we first start, like I said at the beginning, people like x equals a sine theta. And there's no good reason for them to like it. I mean, sine and cosine are a little bit more friendly to work with because, again, the derivative of tangent is secant squared, the derivative of secant is secant tangent, so those derivatives add a little bit of extra complexity. But whatever the trig substitution is, we don't get to pick it. We make the trig substitution based off the particular trouble. And I hope as you look through, the trig substitution tells us nothing about how easy or difficult the trig integral left behind will be. This is a perfect example. This was not, for most people, considered to be a nice trig substitution, but almost everything canceled. We didn't have to do any manipulating, and we got a known trig antiderivative. But here we use tangent, and we ended up getting this left behind. This, again, I don't have the work here. We had the number 8, but then we converted to cosine over cosines and sines. And then either we did a u substitution or we kept manipulating the trig functions. So there are a lot of ways to go here. But this one ended up being a fairly tough trig integral, but it's not because it came out of tangent. Go to this one. We used tangent as the trig substitution. A lot of good things happened. Yeah, we had one little bit of manipulation at the end, but after we cleaned up the trig integral, we were so close to being done. This is a tiny, tiny bit harder than what we had here, but that is almost one of our easiest integrals. And I would say one of the harder trig integrals was number 4. We used one of the more basic trig substitutions. Again, according to some people, they consider that more basic, but you still had quite a mess left. It looked like good things canceled, but that was still quite a mess. You still needed another trig identity, and then you still needed a u substitution after it. So, like I said, you can't decide based off the trig substitution how hard the remaining trig integral will be. We just have to roll with the punches, make the correct trig substitution, clean up as best we can, and then deal with the remaining trig integral.